Hello, this is Brian Kinghorn, and in this video I'm going to tell you about working with balance strategies. And these relate to how to manage the balance between genetic gain and genetic diversity when you're driving Matesel for your breeding program. When you run Matesel, you see in the bottom left graphic this thing we call the frontier. And the frontier, of course, is this slope here, and it is describing for the resources that you've got, essentially your animal or plant population and constraints you've put on the usage of individuals that can be used as parents. For those resources, how far you can push in these two different directions that I'm going to tell you about. The first one on the y-axis is genetic gain or progeny index, typically an index of dollars or monetary value across traits. And we want to get as much genetic gain as possible in the progeny. And basically, this is the average of the parental genetic values as reflected in the progeny. We want that to be high. On the x-axis, we have parental coancestry, and we want that to be low relationships amongst parents, and more parents helps to achieve that as well. So over on the left here, we have high diversity and lower inbreeding in the long term. Now, if we go for a policy of maximal genetic gain, we end up having less diversity and too much long-term inbreeding, and we get that by selecting only the very few individuals as best individuals as parents. On the other extreme, if we select many parents from many different families, we end up with more diversity, but we're digging deeper into the barrel and get less genetic merit in the progeny because we're using less meritorious individuals as parents. And what I'm going to be talking about is how we balance these two key issues in order to come up at a solution. The current solution is shown by this target here with the red trail showing where it has been. And the balance strategy which has been employed in this case is reflected by this green line to achieve getting the solution as close as possible to the frontier. And that happens without other issues being involved, just those two key issues. So that is actually called balance strategy 3, and I'll show you the rest of them in a moment. Here it is, balance strategy 3, a hard constraint and target degrees. The target degrees, that's the way that we have for many years now used a simple description of policy, with 0 degrees being going for genetic gain maximally, and then right up to 90 degrees going for maximum genetic diversity, and we get this curve here. This is actually, in the fullness, it's an ellipse which goes all the way around the screen down here and back up here, but we're only interested in this top left-hand corner with above average value for genetic gain and more diversity than can be achieved otherwise. Right, now what happens when we have adopted a policy of a balanced strategy of target degrees and we start to bring in other issues such as trait and marker distribution management or putting strong emphasis on progeny inbreeding, then we end up getting a worse response for these other two components of progeny index and parental coancestry, and so we move away from the frontier. But with our policy of hard constraint and target degrees, as number 3 is, this green line, the solution mustn't go over to the right of that green line, and that's the constraint we make. It must stay on the left, and it keeps pretty close to that constraint when it gets the result it has. So you have dictated the pattern in which the compromise in these two components of index and coancestry, the pattern of the compromise you make in order to achieve other things, other components in the breeding program. So what I'm going to do now is go and look at showing you that and the other balance strategies on the Matesel interface. But first of all, one we will not look at is the first one, which I've called number 0. This is what we used to use in the old TGRM, and it's simply a weighting factor on coancestry, which is this term here, as opposed to progeny index, which is this term here. And that gives you very little control over the pattern of compromise you get when you bring in other issues, and it's not functionally useful, but it is there for test comparison purposes. And you will see that formula again in the manual with a description of all the other balance strategies available there. So let's now move on to run Matesel. I'll open our classic demo file and run it. And then we'll look at the different balance strategies that are achieved. So first of all, Matesel itself drives the frontier. It seeks to find how far it can go in different dimensions, and that defines the frontier. If in doing that exercise, which you can control, if you click up here on frontier, either in Matesel ini or in the interface, you can determine the number of generations of evolution for each of these points. So you can control how well this frontier is discovered. And if you don't do enough in that, and the solution breaks through that particular point, then the frontier will dynamically be modified to accommodate the better information that you have. Right, now let's go and look at a different policy, a hard constraint on co-ancestry. And that means we now have the maximum permissible co-ancestry text box enabled. So we can put something in there. And let's put in 0.0625 co-ancestry units. And we can see that Matesel gives us the best possible genetic gain given the constraint that you must be lower co-ancestry than that green line. And that's a hard constraint, meaning you can't jump over it at all. If we then go and make a compromise by saying, for example, we want to have the mean in yearling weight increase to a certain amount, which you will discover how to do this elsewhere, but you'll see how I'm doing it right now. So this will be a very small compromise because I haven't asked for too much deviation. If we are a little bit more ambitious and say we want to go up to, in this case, 1.08, I'll put it up even higher. By the time we achieve with the red dot here that, we can see there's much more of a compromise. Now, if instead of having that hard constraint and target degrees, I'd gone for 10, 20, 30, 40. Well, let's try it. 40 degrees on a hard constraint on target degrees. And update. You'll see that even though we would have started in the same place in the frontier before bringing in this constraint, we have now compromised not just in merit, but also in genetic diversity. So we have more merit here at the expense of some genetic diversity. So our policy is such that we have shared the compromise between those two components. And that's a choice for you, the practitioner, as to where you want to be and how you want to make those compromises. However, it does seem sensible to me that you would share the compromise between these two components rather than making it totally based on diversity alone. I'll now say a little bit about how we invoke this target degree line for still working in a hard constraint. The other type of constraint is soft, and I'll tell you about that in a moment. So we want to have higher degrees than the green line in order to achieve our policy, and so it should be on this side, to the left or below. However, as we go down here, it becomes more difficult to keep to the left of it, and so let's just try, if we go for, say, 70 degrees and update that, you'll see the color of the line changes to purple. And now what we're doing, in fact, is pushing to get the minimum possible co-ancestry given a constraint that we must be above this line. Whereas if I go back to where we were before, let's go up to 25 degrees and update. It's a green line, and that indicates that what the program is doing is trying to go as fast as possible for high genetic gain under the constraint that you must be to the left and below of this green line. And that's only done for speed of computation, because if I were sitting down here, let's make it more extreme, at 85 degrees, which is finding difficult to do because of the constraint on yearling weight here is antagonistic. So I shall just take that off by clicking on invoke. It would have worked otherwise if I had not had that on. But now, if it were trying to be down here and moving upwards in genetic gain, most solutions would be illegal because most of them would be above the line as it's pushing upwards, and very few would be to the left. And so it's more efficient to push to the left under the constraint of staying above the purple line. You might want to rewind and listen to that again. And it's not particularly important, but you may wonder why there's a different behavior on either side of 45 degrees, and that is the explanation for it. So let's look at soft constraints. First of all, I'll put our constraint on desired gains upward for target degrees on again. I'll stick with hard constraint and target degrees and go back up to 25 degrees and explain that this is a hard constraint and that we are not allowed to move over to the right of this line. And it could well be, for example, that the algorithm puts up a solution over here. If you had a very slow analysis, it could be that there's a solution right here, a better solution, except for the fact that it just breaks the target degree line of 25 degrees. Then it's a pity that we couldn't exploit that, even though it's a little bit off. And that's where we would go for a soft constraint. Soft constraint on target degrees, and I'll update that. It'll make rather little difference, except that it will accept anything which is on the right of the green line. So let me just make our constraint a little bit more difficult to achieve. And you'll see that it's keeping a little bit to the left of the green line, and that's now so that if it does hop over towards the right, on average it will give us something close to the target degree line for most applications. The only reason you would do this is for speed in applications that are running slowly, because they're rather large, and it does give the algorithm the opportunity to exploit solutions that are good in all respects except that they just break your constraint. And generally, people don't use soft constraints unless they really are working with rather large analyses which are progressing slower than they would like. Now move back to a hard constraint on target degrees. Now I'm going to move on to look at the remaining two strategies, that's number 5 and 6. We've already looked at hard and soft constraints on co-ancestry and target degrees. We didn't actually look at the soft constraint and co-ancestry, but it follows what I said about soft constraint and target degrees. And for project to target degree line, I'm going to open a different file. And this is quite fortuitous. The number of traits in the data file differs from the number in matesel.ini. That's because I've, with a bit of laziness, kept that file in the same directory as the classic demo, and it does have a different number of traits. All I need to do is click OK, and the same for the number of markers being different. This is what that is telling us there. Now the program will run with this new example. And while we're on the subject of those two text boxes that came up, if I were to click the Save button here, it would save Matesel.ini appropriate with the correct number of traits and markers for that file, so you would not have those problems next time. Okay, let me just pause and look at this one. We've got a policy of going for 25 degrees, and it has adhered to that with this solution up here. But if you look at the shape of this frontier, which is different from the previous one because it's based on a different set of animals and conditions, you see that this is not a very sensible place to be, because if we were to take a solution over here, given the shape of this curve, we will be getting a lot more diversity, this amount, at a very small compromise in genetic gain. And this is a more sensible place to be. Of course, you could simply say, I want to be at 10, 20, 30, 40 degrees and move over there. And the program would achieve that for you. But it seems daft that you should have to make that choice and a change of policy to fit that particular circumstance. So if I move back to 25 degrees, I can show you that we can go over there automatically by going to project to target degree line. And the meaning of that you'll see in just a moment. So if I update, so without changing this green line, I've moved over here. Now, why do we get a shape of frontier like this? I'll tell you in a moment. And how does Matesel manage to shove us over here to a sensible place? I'll tell you that in a moment. And when would we use this sort of a policy? I'll also tell you that in a moment. And now I'm going to stop this analysis and go and look at the PowerPoint again. Okay, here's this same picture. And what I want you to consider is that the population we've got has got many lowly related male candidates of similar index value. So we start off here, and it could well be that we're just using one male over the whole population, the very best male. And if we then go and say we're going to add another male, then we've said that there are many lowly related male candidates of similar index values. So if we went to get another male and increase the diversity, say to over here, then because they're similar index value, there's going to be little change in the index value provided by these two males rather than one. And because they are lowly related, we get a big jump in diversity. And as we add more lowly related males with little compromise in merit, then we get this pattern here. The frontier sticks out with quite a pokey bit, with a desirable place to be here. Contrary to this, consider a population where you've only got a few candidates of notably high index value and probably related to each other. So let's say the sire up here is excellent, but the next best excellent sires are his sons. So that as we go and try and increase diversity, we can't use his sons. We've got to look elsewhere. And the other males in the population that are candidates are not so highly meritorious. They don't have such big index values. So to get more diversity, we take a big hit in index. And of course, a legacy sire and a bunch of his sons being the important ones in the population is a sign of a poor breeding program. They probably haven't been using Matesel or a tool like it, and that's reflected in the shape of the frontier. That's the one question answered as to why do we get these different shapes of frontiers. How does Matesel know to go over here? Well, it's quite simple, because this project to target degree line actually looks essentially at this. It looks to see how far we can go up this line as if it were an index on its own. And you can see here by putting a right angle, this is the point which pushes you furthest up this line in the fashion I've shown you. And that's that solution why it is over here, which is a sensible place to be. Number 6, projection plus deviation penalty, basically says I want to be somewhere between strategy 3 and strategy 5, and that puts you somewhere in the middle here. It's just softening that a bit if you're not too sure about going the whole way. Most breeding programs would actually, with any kind of slope of frontier, will tend to give you more degrees than the target degree line when you implement balanced strategy 5. So if you were going to do this in reality, and many people do of course, then you would probably have a policy with fewer degrees, for instance aiming here, because you're going to tend to end up on the right. And that's something you discover for your own populations working yourself. And here if we apply the same policy on a shape of curve like this, it moves to the right, the best solution's over here, but only by a certain amount. Okay, we've gone through those different balanced strategies. Hopefully you got a feel for them. The importance of these last two, particularly number 5, is that we don't have to look at the graph, or if we don't have the opportunity to look at the graph because we're doing batch runs and doing them automatically, and we want to exploit the shape of the curve each time, this is the way to go because it'll do that for you. So especially where you do not have time to look at graphs and you're running batch mode, it's worth doing the research to work out what your policy would best be if you're using project to target degree line. We have now come to the end of this video on working with balanced strategies, but it does leave a question in your head. Where on the frontier should I aim to go? That's a very important question. It's a question for you to answer, not Matesel, but we have a separate video addressing that question. Thank you for listening.